Good morning. Welcome to a sunny but cold morning of Chem 1211 with your host, me, Dr. White. All right, couple things. One, I'm going to be going through some stuff that a little review that I think will help you come final time. Yep, it's coming up soon. And something I didn't do Wednesday that I did yesterday in lab and I'll do now is talk about next week. First of all, by Sunday, I should get all your grades out for the test and also for your extra credit if you handed one in. And next week, I will be spending Monday and Wednesday. On Monday, I'll go over test number 4, like I've done all the other tests. And Monday and Wednesday, I will do my world famous review for the final. Now, if we were face to face, I like that face to face. Never use that again. But anyways, we were face to face in a lab, coming to lab at COD this Thursday or Friday, or next Thursday or Friday, depending you have a lab on Friday. You wouldn't have to come because we have checkup, and I found it was quicker for me to go and look at all the drawers and make sure everything's there and have the students do it. And so I do. And I invite students, if you want to show up and ask any questions, go ahead. If not, you don't have to. But since we're on Zoom, what I will do next Thursday and Friday is it's open Zoom meeting. And what that means is, you haven't figured out, you probably haven't, the Thursday and Friday lab have the same Zoom, just like we do Monday and Wednesday, with the same password. The only difference is you come on Friday, they come on Thursday. I'm going to open it up so everybody can come on Thursday and Friday, ask any questions you have, and also I'll go through some important problems that you should know. And you don't have to come, but I'd highly recommend it. And that's what we'll be doing next week. A week from this, wow, a week from this Monday will be the final exam. Sometime this weekend, I'll put out a announcement and email of the point breakdown and everything for the final exam. Uh, Historically, when I write a final exam, one of the things I do, the material from test 1 is first, then test 2, test 3, test 4. I don't play like a deck of cards and shuffle. I haven't done that in a long time, shuffle a deck of cards. But anyways, I'll be doing it that way. And historically, when we're face to face, my final students are given an hour and 50 minutes, and most are done within an hour and 15, an hour and 20, 25 minutes. Just like my test, you know the material, you should be able to get through it with no problem. All right, any question about upcoming events? Got my speakers on, got to look up there to see, are they on? I have these huge external speakers for this computer. All right, what I'd like to do now before we do the lab is go through some important things that I think would be helpful to you. Not the wrong thing, more wrong thing. All right, everybody see Chapter 6 practice problems on your screen now? Thank you. All right, some things, let's go back to an area where some of you had problems, and I've seen it on the final too. So I'd like to, in the past that is, go through it. Remember we talked about a mole, and test number 2, what is a mole? And one answer, there are a number of them, was the chemist counting unit. And then I also asked, what's Avogadro's number? And that's 6.02 times 10 to the 23rd. And I just remembered I forgot to open something, so I better do that now. Does everybody see one mole of an element equal on your screen? Thank you. All right, this is from important information test number 2, but I'd also highly recommend you go into the lecture folder of Blackboard and look at the file important information final exam. And that will be given to you on the end pages of the final exam. But let's review something first. 1 mole of an element equals Avogadro's number of atoms of that element. 1 mole of a compound equals Avogadro's number of molecules of that compound. 1 mole of an element equals the atomic weight of that element in grams. 1 mole of a compound equals the molecular weight of the compound in grams, and the molecular weight of the compound is the sum of all atomic weights. So if we look at problem number 3, which I hope you all can see. Can you see 3? Thank you. I've been having Zoom hiccups, so that's why I'm asking more today. All right, number 3. How many atoms are 6.574 moles of sodium? What are we trying to find? Atoms of sodium. What are we given? 6.574 moles of sodium. This is the only number we have to start with. We're trying to get your atoms of sodium. So how do you proceed? Well, if you could multiply this number times a ratio, you would get your answer, hopefully. What do you use? You use your good buddy, your good friend, unit analysis. I love that. Anyways, remember, and I hope it has been your good buddy and good friend this semester. Whatever you're trying to get to, the units go on top. Whatever you're trying to get rid of, the units go underneath. Where do you get these numbers? 1 mole of, in this case, sodium equals 6.02 times 10 to the third atoms, 23rd atoms of sodium. Moles of sodium cancel out. You're left with atoms. Remember, when you're doing a multiplication or division, you get the same number of significant figures in your answer as the number you're multiplying or dividing that has the fewest significant figures. And on the final, like the test you've taken, under your name, it will say, please use proper significant figures for all calculated answers. And this has 4 significant figures, 3. 1 is an exact number because it's part of the definition, and therefore it doesn't play a role in significant figures of the answer. So 4, 3, 3 is lower, and that's what you get. And it's time for Dr. White to share the fun. And the question is, how many moles of water are 7.77 times 10 to the 37 molecules of water? And before you start, let me remind you the following. 1 mole of a compound equals Avogadro's number of molecules of that compound. Again, 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules. Have fun. See what a nice guy Dr. White is. He shares the fun. If I say fun enough times, you might believe me. I think it's working too. I see smiles on people's faces. Oh, it warms my heart to see everybody working on their mold problems on a Friday morning. Thank you. Public service announcement from Dr. White. Don't forget, if you haven't gotten it, get your vaccines. I know a couple of you told me about stories of not unpleasant side reactions. I was surprised I had none. Hope they weren't injecting me with water. No, I don't think so. Anyways, uh, but really get your shots. They're widely available now, and the government's paying for it. All right, I think everybody's done. So I better get to work. All right, let's take a look at this. And the question is, how many moles of water are in so many molecules of water? So what are we being asked to find? Moles, water. What are we given? This. How many molecules of water are there? And therefore, this is the only thing I have to start with. So guess what? I'm going to start with that. If I could convert it by some ratio, what units do I want my answer to be? Well, we figured that out. Moles of water. And now it's time to use our good buddy, actually my good buddy, hopefully your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And where do I get these two numbers? 1 mole of a compound is equal to Avogadro's number, 6.02 times 10 to the 23rd. Notice molecules divided by molecules, anything divided by itself equals number one, which means it's gone. So that cancels out. I'm left with the right units. Before we go to our calculator, Dr. Whiteson is right again, three significant, three. The one is an exact number. So my answer should have three significant figures. So it's time to go to the calculator. And if we put in, and let me just check, everybody see my spreadsheet? Thank you. I have my numbers in, I hit enter, I get this number. And remember, we're supposed to have three significant figures. I'll let you round it off first, then I'll do it. And let's look. Keep the one, keep the two, keep the nine. That's our three significant figures. Use the zero to round off. That's four or less, or five or higher, and four or less. So I drop all that. It's 1.2 29 times 10 to the 14th. And that's your answer. And as I haven't said in a while, but I think all of you know by now, if you have any questions, feel free to ask always, because in my class, there's no such thing as a dumb question. Not only in my class, in my whole world, there's no such thing as a dumb question. All right, everybody see what is the molecular weight of, thank you, of sulfuric acid? Let's go through this, a quick review. Remember, the molecular weight is the sum of all atomic weights. And if you look at the formula for H2SO4, sulfuric acid, is 2 hydrogens, 1 sulfur, 4 oxygens. You have 2 hydrogen, 1 sulfur, 4 oxygen. So it's 2 times atomic weight of hydrogen. And a quick review, because you haven't done it in a while. Everybody see periodic table? Thank you. And if we look at hydrogen, and underneath your name, just like test 2, 3, and 4, we'll on the final say, please use all atomic weights to 3 significant figures. And if I blow this up a little, that's better. You can see hydrogen has 1.008, that's 1.01 to 3 significant figures. Oxygen is 15.999, and that's 16 to 3.0 to 3 significant figures. Sulfur, as you can see, has 32.066. I'll let you first have fun, round that off to 3 significant figures. And let's do it. We have a 3, a 2, and a 0. Those are 3 significant figures. Remember, 0 after decimal is always significant. And we use the 6 to round off. So have 4 or less, or 5 or higher, and 5 or higher. So I'm going to drop the 2 6s, change the 0 to 1. So that the 3 significant figures is 32.1. So now, if we look at 2 hydrogen, 1.01, 1 sulfur, and 32.1, the bracket fell off here. I'll have to look for it on the floor later on today. But anyways, oh, that was awful joke. I'm not going to use that again. But anyways, 4 times 16.0. Remember, 4, 1, and 2 are exact numbers. So I have 2.02, 32.1, and 64.0. I add them up, there's an extra dot in there, forget about it. It's 98.12. However, when you add numbers, you have the same number of significant figures to the right of the decimal as the number that has the fewest significant. So notice 2, 1, 1. 1 is the smallest or lowest number, and therefore you should have 1 significant figure past the decimal. Everything on the left, to the left, leave alone, just add up like normal. And so if we look at this, keep the 1, use the 2 to round off, it's 4 or less, I drop it, and that's 98.1. And that's how you get the molecular weight of a compound. And why do you need the molecular weight of a compound? If we look at problem say 16, how many moles are 2.345 grams of ammonia? We're trying to find moles of ammonia. We're given a weight, grams of ammonia. And let me remind you, and important information, this will be for the final, but I'm showing you from test number 2, is 1 mole of a compound equals the molecular weight of that compound, and the molecular weight of the compound is the sum of all atomic weights. So remember, 1 mole of a compound equals the molecular weight of that compound in grams. So if we have this amount of ammonia and we want to get the moles of ammonia, we use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of, grams of ammonia, goes underneath. And where do we get the ratio of moles to grams of ammonia? 1 mole of ammonia equals the molecular weight. And right here, the molecular weight, the sum of all atomic weights, 3 hydrogen, 1 nitrogen, 3 times 101, 1.01, gives you 3.03. Nitrogen atomic weight, the 3 significant figures is 14.0 times 1 is 14.0. Add them up. Notice 2, 1 past the decimal, you drop the 3. 1 mole of ammonia is 17.0 grams. That's how we get the number. And grams of ammonia cancel out. You get moles of ammonia. 4 significant, the 1 is exact. This is 3. My answer is 3 significant figures. And with that, I'm going to let you have some fun. In case you don't have your periodic table handy, the atomic weight of hydrogen, 1.01, atomic weight of oxygen, 16.0. Have fun. Forgot the question mark. Isn't the silence deafening? And when you're done, give me a thumbs up. And when you're not done, give me a thumbs down. Oh, they don't have a thumbs down symbol. Remember, Dr. White created a new word. Instead of using emoji, I'm going to use symbolic. Yeah, I'm going to try this one again too. All right, looks like everybody's done. So let's proceed. The question is, how many grams of water are 8.12 moles of water? And what are we trying to find? Grams of water. And I hope by now everybody knows H2O is water. If not, and we have 8.12 moles of water. And therefore, this is the only thing we have to start out with. So guess what? I'm going to start with that. Now, if there was some magic ratio, I could multiply this 8.12 moles water. What units do I want my answer to be in? And we figured that out right there. Grams of water. And now it's once again time to use your good friend, your good buddy, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And where do we get these two numbers? Well, if you look at important information, in the past students had to memorize this, but I don't do that anymore. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. So 1 mole equals the molecular weight in grams. Well, what's the molecular weight of water? Well, it's the sum of all atomic weights. Well, there's 2 hydrogens and 1 oxygen. And this is 2 times, as I showed you up here, your atomic weights. And you can get this from the periodic table to the 3 significant figures. That's 1.01. For oxygen, it's 16.0. Do the math. It's the sum, so I'm going to add these two together. I get 18.02. This has 1 past the decimal. This has 2, which is a smaller number. Hopefully you pick 1. So I keep the 1, use the 2 to round off. That is 4 or less. I'll drop it. So this is 18.0. And now notice moles divided by moles cancel out, because anything divided by itself equals number 1. And now I can go to my calculator and find out the answer. And remember, this is 3. I'm in my rut again. 3 significant, 3 exact number. My answer should have 3 significant figures. If I come over here, That's one number. I could also do it in scientific notation. And either way, you're going to get the same answer. Let's look at in the yellow, 1.46160000 times 10 squared. Round that off to 3 significant figures. You go first. Time's up. Keep the 1, keep the 4, keep the 6. Use the 1 to round off. The first 3 are significant figures. The next number is what we use to round off. That's 4 or less. I drop it. So it's 1.46 times 10 squared. Or if you look at E1, it would be 146. Either way would be the right number. And that's your answer. And that's how you do that. And that's how you use your good buddy, your good friend, unit analysis. Now, if we look in chapter 8, where we have more complex reactions or problems to deal with. And let me do this. And the first one is, let's look at this. For the following reaction, C3H8, propane plus oxygen gives CO2, carbon dioxide, water, and I don't have it up there, plus heat. That's combustion. C3H8 is propane. And what I would like to remind you, the coefficients, the number that goes in front of a balanced chemical equation, are the molar ratios for that reaction. And when there's no number in front, coefficient is assumed to be, not assumed, it is 1. So 1 mole of C3H8 reacts with 5 moles of oxygen to make 3 moles of CO2 and 4 moles of water. Again, the coefficient, the number in front of the chemical formula in a balanced chemical equation gives you molar ratios. And for this reaction, 1 mole of C3H8 propane reacts with 5 moles of oxygen to give 3 moles of CO2 and 4 moles of water. And now the question is, how many moles of oxygen are needed to make 23.33 moles of CO2? And what are we trying to find? Moles of oxygen. What are we given? Moles of CO2. So here we take what we're given to start with. What units are we trying to get to? Moles of oxygen. And therefore, if I had a ratio to convert moles of CO2 to moles of oxygen using your good buddy, your good friend, unit analysis goes on top, moles of CO2 goes underneath. Where do we get these numbers? From the balanced chemical equation. And notice for every 5 moles of oxygen, we make 3 moles of CO2. So the ratio is 5 moles of oxygen, 3 moles of CO2. These are 3 and 5 exact numbers. This is 4, this is 3, this is a mistake. Sorry. That should be 4 significant figures. It ain't. Oh, that's not proper. It is not. And that's my mistake. All right. Why don't you try number 2? First of all, can everybody see number 2 at the bottom of the page? For the following reaction, 4 moles of ammonia, 3 moles of oxygen, make 2 moles of nitrogen plus 6 moles of water. How many moles of NH3 ammonia are needed to make 4.58 moles of nitrogen. Your turn. Boy, I'm working you hard this morning, everybody. Where's my whip? Get to work. That's right. I got to buy a new bullwhip. The last one died. My first one was such a beautiful bullwhip. In case you don't know, and you should be very careful around me, Dr. White is into unusual weapons. Like boomerangs, nunchucks, bullwhips, wet noodles. No. It reminds me of one of my favorite all-time TV shows, which you probably don't know. Anybody out there ever see any episodes of the great TV show Kung Fu? You don't even know what I'm talking about. How sad. All right, I think everybody's done. Let's get going. And let's take a look at this. How many moles of ammonia are needed to make 4.58 moles of nitrogen? So what are we trying to find? Moles of ammonia. What are we given? Moles of nitrogen. This is the only number we have to start with. So I'm going to start with this. What if I can multiply this number by a magic ratio? It's not magic, it's chemistry. What units do I want my answer in? Moles of ammonia. So I have that here. And now it's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top, the units, and whatever units we're trying to get rid of go underneath of this ratio. Where do we get these numbers? From the balanced chemical equation. For every 4 moles of ammonia, we make 2 moles of nitrogen. The coefficients of a balanced chemical equation tell you molar amounts. So for every 4 moles of ammonia, we make 2 moles of nitrogen. And these are exact numbers. And therefore, 3 significant, oh, I got it right this time, 3 and moles of nitrogen divided by moles of nitrogen cancel out. And that's how you do it. All right, let's look at the following. Everybody see number 4 on their screen? Thank you. All right, the question is for a following balanced chemical equation. Doesn't say balanced, but I'll always give you a balanced chemical equation. I had a chemistry instructor who didn't, and first had to balance it, but I won't be that mean. And here we have how many grams of hydrogen are needed to make 125.6 grams of hydrochloric acid, HCl. What are we being asked to find? Grams of hydrogen. What are we given? Grams of hydrochloric acid. There's no way you can go from grams of HCl directly in one step to grams of hydrogen. You need 3 steps. And if you look at important information from test 2, which also will be in the final, mass calculation for reactions. Remember, mass means grams. And step 1, whatever you're given the mass of A, you convert to moles of A. We just did that earlier, but we'll do it again. Step 2, whatever you have in moles of A, you go to moles of B with a product you're trying, or the answer you're trying to get to. We just did that. And finally, earlier today, we did this. Now that you have moles of B, you convert to mass or grams of B. So the first step, we have grams of hydrochloric acid. We want to convert it to moles of hydrochloric acid. Here's the ratio. We'd have to multiply. How do you get that ratio? Moles of HCl using your good buddy, your good friend, analysis goes on top. Grams of HCl go underneath. Where do we get the numbers that go in this ratio? 1 mole of a compound equals its molecular weight. And the molecular weight of HCl, hydrochloric acid, is the sum of all atomic weights. 1 hydrogen, 1 chlorine. Here are the atomic weights, the 3 significant figures. It adds up to 36.51, rounded off because you have 1 and 2 significant figures to the right of the decimal. 1 is smaller, that's 36.5. And therefore, 1 mole of HCl is 36.5 grams for 3 exact number, 3 significant figure answer. Step number 2, whatever you have now in moles, you're going to convert to moles of what you're trying to get the answer in this case, hydrogen. And how do we do that? Well, we just figured out we have 3.44 moles of HCl. We want to go to moles of hydrogen. We take and put, using your good friend, your good buddy, your analysis, moles of hydrogen go on top. Moles of HCl go underneath. Where do we get these numbers? What's the relationship between hydrogen and HCl? When there's no number in the coefficient of the reaction, it's 1. Therefore, 1 mole of hydrogen makes 2 moles of HCl. 1 mole of hydrogen makes 2 moles of HCl. We get those numbers from the balanced chemical equation. And notice here, 1 mole of hydrogen makes 2 moles of HCl. These are exact number, three significant figures. Are we done? No. We have grams of hydrogen we want for our answer, but we got moles. So we're going to do step 3. Moles of B, in this case hydrogen, will convert to grams of B. And again, using your good buddy, your good friend, analysis, whatever we're trying to get to, grams of hydrogen goes on top. Whatever we're trying to get rid of, moles of hydrogen go underneath. Where do we get these numbers? 1 mole of a compound equals the sum of all atomic weights in grams of that compound, and the sum of I'm getting ahead of myself. 1 mole of a compound equals the molecular weight of that compound, and the molecular weight is the sum of all atomic weights. And hydrogen, they're H2 gas, hydrogen gas is 2 hydrogens. Each atomic weight of hydrogen is 101, and therefore it's 202. And therefore 1, 202, that's how I get the numbers, 3, 3, exact number 3. Now, if you notice, I have 3.47 or 3.48 for this problem. And that's because when you have multiple calculations like this, there's two theories on how to use significant figures. One theory or group or practice is round off at each step. The other is round off at the end. Dr. White is a round off at each step person, but I'm not going to force you to do what I do. So I will calculate, as you saw in test 2 and 3, and there wasn't that chance in test 4, but on the final, I will do both, and therefore you can possibly have two different answers. And that's a little something I thought I'd go over this morning because we've already done all the problem sets. And what should I do with you people this morning? I figured that would help you. Now, I think I might have mentioned it Wednesday, but I know I mentioned it again yesterday, so I better do it again today so you people don't feel left out. And that is, how do you prepare for the final? The best way is use your hourly exams as practice problems for the final. Will I give the same problems? No. Will I give similar ones? Of course. Look at my practice problems. Aren't there similar problems on each test that you practice? Because that way you do well. And that's how I do it. So I'd highly recommend and start now, even though next week I'll be doing a really thorough review. But as I said, the first day of class, if I give you the DVD or Blu-ray, let's go high class Blu-ray, how to ride a bicycle, you don't know how to ride a bicycle, and all you do is watch my Blu-ray or that Blu-ray. When you get on a bicycle, you're going to fall off. But if you practice, you get better. Same thing you've learned this semester. Do practice problems. I would go back and do the test 1, 2, 3, and 4 as practice problems. And before we take our break, I'll ask, are there any questions? Ooh, that reminds me, I'll say this again on Monday. On the final exam, everybody write this down quick, there'll be balanced chemical equation problems, probably 12 points, so know how to do that. We'll go through it in the review next week, but I thought I'd just tell you that. And with that, it's time for a break. I'll see you at 9:55. We'll come back and do a wonderful lab. I'll be back in 5. Time to start again. Train's leaving the station, so get on board. You haven't figured out by now, Dr. White's a train enthusiast. I have been since I was 4 or 5 when my father took me one Sunday morning to the south side of Chicago train yards. We spent the whole morning. This is back when they still had steam engines. Oh, were they big, huge beasts, exciting to watch. And we just watched them by the area where they did maintenance and were moving the engines back and forth for a couple hours. It was still one of the greatest mornings of my life. But anyways, let's get moving. In the United States, whether you're in an academic lab, a research lab, or in a chemical plant, and one of the things you do a lot is make a standardized solution of sodium hydroxide. And the sodium hydroxide solution, certain molarity, and knowing what that molarity is exactly is very important for titrating various solutions, as you learned last week's lab, unknown HCl solutions that you make up, and a whole lot of other things are done, especially in quality control labs at chemical companies. I've managed them, I know that. So, question is, if you take and put in a certain amount of sodium hydroxide, which is a solid at room temperature, and mix it with enough water to make 1 liter of solution, dissolve all the sodium hydroxide, you do that in a volumetric class, are you really sure what the molarity is? And the answer is no. You just can't say I have so many grams sodium hydroxide. You standardize it. And how do you standardize it? By a titration. And that's today's lab. Everybody sees standardization. Sodium, thank you. And today's lab, like I have here, if you make a specific molar solution of sodium hydroxide, how do you accurately know what the molarity, I guess I should have put it, how do you know accurately what the actual molarity of the solution is? You do a titration with a standard monoprotic, that means it's an acid that just has one acidic proton of a known number of moles. And the universally used standard monoprotic acid for standardizing sodium hydroxide is KHP. KHP stands for potassium hydrogen phthalate, but everybody just calls it KHP, and it's a solid. And KHP reacts with sodium hydroxide in the following reaction: sodium hydroxide, KHP, salt water. This is a neutralization reaction you learned in the last chapter on acids and bases. And at neutralization, that's when the pH indicator changes color. The following is true: moles of KHP equals moles of sodium hydroxide. Now, since KHP is a solid, you know, if you have so many grams of KHP, you can convert it into moles using unit analysis, which I wrote the equation, the moles of KHP I put on this side, normally you see it on the right, is equal to grams of KHP times 1 mole of KHP for the molecular weight in grams of KHP. Being the nice person I am, the molecular weight of KHP is 204, the 3 significant figures. Therefore, if you know the weight of KHP in grams and divided by 204, you'll get the moles of KHP. So here we have moles of KHP. Now, if you remember, for acid-base titrations, we had moles acid equals moles base. And important information, I broke that down further. Moles, milliliters of acid times molarity of acid equals, I'll write it down here, milliliters of base times molarity of base. And because the 1,000 is on both sides, we could do this. But for this one, we need to put, remember, molarity of NaOH equals moles NaOH for 1 liter or 1,000 milliliters. So with this, I can put in milliliters, and the molarity, I'll use this, and that's how I get this equation. The moles of KOHP, the acid, which you get from this equation too, equals milliliters of NaOH times moles per 1,000 milliliters of NaOH. Now, if I calculate the moles of NaOH, and since it's per 1,000 milliliters, that's also the molarity, which leads us to calculation. If you solve for moles of NaOH, would be that equation 3, which is also the molarity. So you'll be using equation 2 and 3 and a titration to determine the molarity of sodium hydroxide solution. Unknown, because you don't know what it is. Now, one important thing is whenever you're doing a titration or other measurements that are very important, you always do it in duplicate. That means two. I'm getting dizzy now. Hold on, 2. And oh, look out, it's totally worthless humor Friday. I wonder how many adjectives I can come up with saying how bad my humor can be. Lots, I'll bet. Anyways, when you do a titration, you always do it in duplicate too, because that allows you to determine, did you do it right? If the numbers are almost the same or exactly the same, the answer is yes. If they're not, they're way apart, you made a mistake and you better just repeat everything. So that's why in this lab, you'll be doing 2 titrations, two titrations. By the way, when we're face to face, Dr. White's, this is obnoxious. All right, I've logged into Beyond Lab Z, clicked on the chemistry. Does everybody see welcome to virtual chem lab? Thank you. Now, scroll down just like last week in the lower left corner. Everybody see acid-base chemistry. Click on that. It's in the instructions that are in the lab. I'll show you that in a little while. Dr. White tries to make things easy for students. And you scroll down. Let me move this out of the way. To acid-base standardization. Everybody see that where my pointer is on the screen? You click on that. And we get to hear the great sounds from Beyond Lab Z. Now, here's the lab. In the burette, they already have unknown number 8 in there. You can see the liquid right here. But the first thing you'll do is, where it says drawers, open it up. Oh, sound effects. Move this out of the way. Take the beaker, and you're going to put it over there right next to this brown jar, which has KHP, potassium hydrogen phthalate. Say that 5 times quickly. No, you don't have to. Now, click on the balance to zoom in on that. Everybody see where I am. Take the weighing paper, put it on the balance, chair it, which means zero it. Take the cover off. This is all in the instructions. Now, something I learned last lab after I wrote it, which I learned for this lab because Dr. White finally read the instructions. Sometimes I feel I don't need to read the instructions. I miss certain things. Take your spatula And then see the different pictures here? Put it by in here and then hold it there. And see how it's full now? Hold it over here till it snaps up. Come on, snap up there and let go. You want about 2 grams, so you need 2 spatulas. And hold it by the bottom symbol of the full spatula. It's snapped in place. And notice I have about 2 grams. You'll need to record this weight. I'll show you a table I gave you. And this is in the instructions. Now you take the weighing paper and bring it over to the beaker. Dump it in. Yay. Now, see where it says zoom out? Zoom out. Now, you need to put water in here. Now, if we look at over the sink, we have 2 water taps. One, you can see the little green knob, and there are 2 knobs. This one, you can't even see the knob, but it was usually silver with the white tip. The 2 knob, this lower tap, is for what we call in the chemical industry city water, tap water, which has a lot of ions in it. You don't want ions in your water unless you're drinking it. And so we use the back tap, which is deionized water. Grab your beaker, put it underneath, hold it for about, everybody hear the water? It got great sound effects. And put it in here. Oh, by the way, I forgot to do this so you don't run into the drawer and hurt yourself. I'm going to close it, which I just did. In real life, I told students, don't, leave your drawers open. It hurts if you walk into it, and it does. Now, we're going to use the indicator phenolphthalein. Phenolphthalein is a pH indicator that changes color from clear to red, or a very light red or wine color when you're at exactly 7.0 plus 1 molecule, the slightest space to see. Now watch carefully, this is real tricky. I describe it. Click on the bottle, see how I have the eyedropper. Now, you've got to bring it here. Nope, didn't do it. Come on, snap up. There, see how it snapped up, jumped up? If it doesn't do that, you're not having anything. I found that out a couple of days ago. How come it's not changing color? And I realized you gotta let it snap up. Now, over here, you see the burette, upper left-hand corner? The bottom of the U, that's called the meniscus, is right on 0 line. Each one of the smaller lines is 1/10 of a milliliter. You can get 3 significant figures. So I'm starting at 0.00 for this one. Sometimes they have you start at 0.05. So make sure you record that. Now, you don't have to, but I think it's cool. But I'm a chemist. Put a pH probe in there. And this will also show you the pH. And as you learned last lab, burette has a stopcock, and you can add at fast or slow rates. I'm gonna go take a walk around the block. Oh, what did I just do? That was weird. Let me move this down here. Let me get this over here. And you don't have to use it, but when that starts going up, you can tell you're near the, everybody see the graph over here? When that starts inching straight up this way, like a corner, that means I'm near my endpoint. The endpoint is when you're near, when moles of base equals moles. Let me do something. That should work better. And you might want to do this the first time, shotgun it, like I taught you last week, to get the approximate, then two more accurately. You notice it's slowly going up. And I'm looking at the beaker now to see when there's a color change. And I can even go slower. Should change right about now. How do I know? It's because this is starting to arch up. And there you go. Everybody see that faint pink color? That means I nailed it. But Dr. White's done about 1,000 or more of these, so I've done it. Now, if you go past the endpoint, first of all, at this point, this is the final volume. And notice I'm at 33.95. I'm right before 34. This is a 33.9. I'm roughly halfway between 33.9 and 34.0. Now, watch carefully. If you keep on going, it's going to get redder. See how it's redder? And you can go past the endpoint. But if you go a little past, that's part of learning how to titrate. Dr. White's done enough of these that I know how to do these accurately. And now you record the final volume that I had before. If you notice here, as soon as I saw this inching up going this way, I knew I was near my endpoint. And I've done it where you don't have a pH meter and you're just careful. And it takes time. Titrations are an exercise in patience. If you're not patient, you're not going to get good results. And that's true. Now, you're going to do it twice. And the fastest way I figured out how to do this is exit and start again. And you go through the same procedures. Everybody see the procedure there? And what I just showed you is written here. Here's where you use the scoop like I showed you. Record the weight, drag the beaker over to the tap, fill it, put it back on the plate underneath the burette. That's a magnetic stir. I like to put in the pH probe, add the phenolphthalein. Note I have here move eyedropper and beaker until it snaps up, and then it will add it. Record initial volume, add NaOH until the solution turns a light red, and stop, exit, and repeat those steps again. Now here, for each titration, you'll measure the grams of KHP, which is about, should be near 2 grams. You'll have moles of KHP, which you use, don't get dizzy while I'm running up quickly. Equation 2, and then you'll have your initial and final burette reading volume. I figured you could figure out final minus initial is the volume of NaOH you use, and the molarity of NaOH you use equation 3, which is right here. Moles of KHP times 1,000 divided by milliliters of NaOH. And you'll write in the molarity right here. Now, good news, I've got some questions for you to answer. And let me tell you something important about KHP. KHP is hygroscopic, means it likes to absorb water. And when you work in a lab using KHP, whether it's an academic, industrial, or research lab, which is also industrial or could be academic too, it's always important to keep your KHP dry. How do you do that? You put it in a hot oven to keep dry it. After you dry it, you put it in a desiccator. Ooh, it's time for Dr. White's show and tell. Everybody see this pictures on your screen? Thank you. The center, this one right here is a good one. I use these type, and it's heavy glass with a lid that's, you use high vacuum grease to keep it sealed so no air gets in there, no nothing gets in there. And here's a plate, you put your sample underneath, you put a dryer, a desiccant, and the most common one is dry right. I forgot what they make it out of, calcium chloride or something like that. And it's usually colored blue. And when it goes pink, it means it's absorbed too much water. You got to put it in the oven and get the water off the dry right. But anyways, right before, after you heat it, you put it in here, let it cool, and keeps it dry. Because you don't want wet KHP. That's going to throw your whole calculation of how many moles of KHP off. And because of that, Dr. White got sneaky. Notice number 5. Everybody see number 5 on the screen? And number 5 is KHP can absorb water if it's not kept in a desiccator and put in an oven to dry before using. Explain what would happen to the, notice I have an underlined, the numerical value of your sodium hydroxide solution results if you had wet KHP. And that's something for you to think about. And with that, if I look at the clock, we're done early. I'm done. Well, actually not. I have lots of tests, extra credit, labs to grade the next couple of days. But anyways, you guys are worth it. With that, I'm going to say, gang gesund. Goodbye. I'll see you on Monday.